Music is all about setting up expectation and then either fulfilling that expectation or denying it, right? And that's where the tension comes in the music. And I feel like if you do that in education as well, it makes for an exciting class. Like right now, or at least a few seconds ago, I was doing this, a lot of tension, expectation, and then I did absolutely nothing, right? I denied it. What? Song of the day? Well, it's Thursday, so we don't have one. What? No one likes the song of the day. I play music and you guys are like, this sucks. All right. Well, here. How about this? I don't know what you're saying and I don't care. All right, so this is the number that you can type in on Spotify. If you go to the search thing, and that'll pull up me. It'll be a picture of me in a Blues jersey. Back when I had a shorter beard and I think shorter hair too. But anyway, that's me. If you go on there, you can find all my playlists, which I have a million. Whenever I find a new album, I'm making a playlist, and it's one of the albums I listen to a week. I listen to 4 albums minimum every week, new albums. So I got a lot. What you want to go to is go way down, keep digging, and find where it says Song of the Day 2019, 2020. That'll be your class Song of the Day. So you have a playlist for all this stuff. Okay. Also, send me music. All right? Why not? You get to see all the crazy, ridiculous music I listen to. All right. So that's it right there. So let's review for the quiz tomorrow, because the quiz is on Friday, right? All right. Weak stuff. All right. Define each term: transversal, corresponding angles, etc., etc., etc. Didn't we just do this for homework? You have questions on it? Okay. Well, let's skip that for now. Turn the page. There we go. Using only corresponding angles postulate, CAP, vertical angles theorem, VAT, linear pair theorem, LPT, definitions, and any of the properties of equality complete the following proofs. So basically what I'm saying here is you're not allowed to say, oh look, 3 and 6 are congruent by alternate interior angles theorem. Done. Because they're alternate interior angles, right? They're opposite sides. That's alternate interior, meaning the interior, right? Yeah, I win. You're not allowed to do that. You have to use CAP, VAT, and LPT. That's what we've been doing, right? What? Okay, good. So it says prove angle 3 is congruent to angle 6. Well, that's what we did like 2 days ago, right? You know. So 3 and 6 are those angles right there. Can we see what's going on? Do I need to show the directions, or can you? Okay, wonderful. Excellent. Perfect. Okay, so I'm going to zoom in down here. 3 and 6. Okay, so first of all, we're given that these lines are parallel. That's what this stuff means, right? So let's write that. Given. What do you want to call these lines? Give me a letter. L and M. Nice. Had an opportunity for a joke there and you didn't take it. I appreciate the maturity. All right, given L is parallel to M. And we have that given for all of these, so I'm just going to write that down now. Why am I making you write this down? First of all, if we aren't given that those are parallel, then none of these things are true, right? The only thing that's true is that the corresponding angles will be congruent. Everything else doesn't follow. So you need that information. Second of all, it'll be worth a point on the quiz. And that's super easy. One of y'all, at least, won't do it. And you're going to miss a point on each of these. All right, so 3 congruent to 6. The way we're going to do this, at least the way I would do it, is I would say, look, 3 and 7 are corresponding angles. So they are congruent by corresponding angles postulate, yeah? Remember corresponding angles are the ones that are in the relative position? See how they're both in the bottom left corner? Mm-hmm. And then I would say 7 and 6 are congruent by vertical angles, right? So 3 is 7, 7 is 6, therefore 3 is 6. That's the game plan. Do you see the game plan? Wonderful. All right, so angle 3 is congruent to angle 7 by corresponding angles postulate. It's the postulate that says if we have corresponding angles and the lines are parallel, which they is, then we know that they're congruent. So far, so good? Yeah, you know I'm mocking you. Jenna knew. All right, so we know 3 and 7 are the same. What's 7's relationship to 6? They're congruent. How do we know that? Vertical angles theorem, very good. So 7 is congruent to 6 by vertical angles theorem. Guys, this is the quiz. So check it out. If I know that 7 is the same thing as 6, and there's a 7, right? Good God, I hate this gap right in the middle. Why did I tape the paper right in the middle of the table where the gap is? 7 and 6 are the same thing. I can switch them out, right? So instead of writing 3 is congruent to 7, I can rewrite that as 3 is congruent to 6 by substitution, right? Now, is that arrow required for your proof? No, I'm just doing it to teach, okay? 'Cause people are still struggling with substitution a little bit. So instead of writing this guy as angle 3 congruent to angle 7, I'm going to write congruent to angle 6 by substitution. Ta-da! I did it. I did it. I win. Did you win too? What if I taught my class like Blue's Clues? Where I like just waited for a response and then was like, oh, good, and no one talked? It's basically what I do anyway. You'd rather Dora? What should we use next? Substitution? Vertical angles? Or cap? Substitution? Vertical angles? Or cap? Cap! Good job! All right, so that was 2. I could do it. How you feel? Great. That's the quiz. Let's go down. Let's take a gander at number 3. It says angle 1 and angle 8. Well, let's find them on our diagram. Angle 1 is this one, and angle 8 is that one. Ooh! Alternate exterior angles. My favorite. All right. How are we going to prove 1 and 8 are congruent? What's the game plan? Somebody walk me through what their thought process, because it's not always my way. Yeah. Okay, Michaela, sure.
Angle 1 plus angle 2 equals 180, and angle 7 plus angle 8 equals 180.
Okay, so this is what we did last week. This is less efficient than my method, but it totally works. So check it out. 1 and 2 are 180. 7 and 8 are 180. How? By definition of linear pair. We're allowed to use definitions, right? Line L has 2 angles on it, the top part, right? They're a linear pair. Oh, check it out, okay. Right? So, linear pair. That's what a pair looks like, right? Totally? That's a pair. That's a pear. It's not perfect produce, but we should buy ugly fruit. Okay, it's still going to taste good. That's a pear. Now, a linear pair means it's a line, right? So imagine we take this pear, right? We squish it down. It's flat now. But it still has the stem. It's a linear pair. It's free real estate. It's a linear pair. It's a pear that's been squished down, but the stem's still there. Is that what we have here? Oh, yeah. So 1 and 2 are linear pair. Get it? Do you get the joke? Yes. Pair and pair. Pairs are just bears flipped upside down. Yes. Nope. Nope, I won't do it. All right. You can't make me. That's a pair. That's a linear pair. But with a stem up. Thank you. All right. So, yeah, I know. So 1 and 8, let's go back. 1 and 2 are linear pair. 7 and 8 are linear pair. By definition, right? By linear pair theorem, they add up, they're supplementary. And if they're supplementary, they add up to 180 by definition. And if they add up to 180, then they add up to each other. So 1 plus 2 equals 7 plus 8. We know 2 and 7 are the same thing because reasons? Do you see the problem here, Michaela? You have to then prove that 2 and 7 are the same thing. So you can subtract them, make them go away, right? That would be the next thing, right? 1 and 2 add up to 180. 7 and 8 add up to 180. So these guys equal these guys. Well, in order to subtract these guys and get 1 and 8 on their own, you need to prove that 2 and 7 are the same thing. So we have to prove 2 and 7 are the same thing, which is really the same thing as proving 1 and 8 are the same thing. You see what I'm saying? So we have to prove those and then go back and get these. Not as efficient. Here's what I would do, okay? I would say, look, 1 is the same thing as 5 by cap, right? And 5 is the same thing as 8 by vertical angles. Therefore, 1 and 8. Yes, ma'am.
Could you do that 1 and 4 are congruent by vertical angles and 4 and 8?
Beautiful. Excellent. Thank you. Yes. 1 and 4 are vertical, so they're congruent. 4 and 8 are cap, so they're congruent. Therefore, 1 and 8, right? Lots of ways to do it. Lots of ways to do it. Some ways more efficient than others, okay? So your way would work, but it would require you to do the same work we're doing anyway, because you'd have to prove 2 and 7 are congruent. How would you do it? 2 is 3, 3 is 7. Then switch. You see what I'm saying? Yeah. Yes. 1 is 5 by cap. 5 is 8 by vertical. Therefore, 1 is 8. Now let's write it. That's the game plan. That's literally the proof, but let's actually write it. So we said 1 is congruent to 5, and that's by cap. You could also do 1 is congruent to 4 by vertical angles, and then jump down. That's what she did, right? So 1 and 5 by cap. Then we know that 5 is the same thing as 8. How did we know 5 was the same thing as 8? Vertical angles theorem, right? I don't structure the course, but if we were doing proofs my way, we would have done this before the other proofs, because I think these are easier. Oops. Actually, you know what? Forget that. I'm going to do what I want from now on. All right. They're the same thing, right? So I can switch out 8 for 5. So I'm going to do that. 1 is congruent to 8. By substitution, we are done. What do you think? Wonderful, Jenna. Glad. All right. 4 and 7 supplementary. Let's find 4 and 7. 4 and 7 supplementary. Okay. Well, here's the problem. 4 is on one intersection, 7's on the other. So we need to bridge them together. That's going to be cap, probably, to bridge them, right? Which theorem lets us say something supplementary? Linear pair, right? So we should probably start out with a linear pair. Right? So 4 and what? 4 and 3. And he picked 4 and 3 to be the linear pair. He could have picked 4 and 2. But notice 2 doesn't have a relationship to 7, at least not a very easy one, right? If he picks 4 and 3 to be the linear pair, which they is, then 3 and 7 we get by cap, right? Small one of 7 in there. So 4 and 7 are a linear pair. That means they're supplementary. 3 and 7 are the same thing by cap, right? Corresponding angles postulate. And so, therefore, 4 and 7 must be supplementary. So I'm going to write that. Okay? Angle 4 and angle 3 are supplementary. And we know that by linear pair theorem. Now, last week we had to prove they were a linear pair to begin with, right? And we did that by saying, look, they're collinear, right? Therefore, they're a linear pair. Therefore, linear pair theorem says they're supplementary, right? But we're cutting to the chase here. We know they're a linear pair. We're all smart enough to know that now, I hope, right? They're sitting on a line together. Linear pair. Okay? So 4 and 3 are supplementary by linear pair theorem. We know that 3 is congruent to 7. Why is 3 congruent to 7? Yeah. By C-A-P. Corresponding angles postulate. 3 and 7 are corresponding, right? Bottom left, bottom left. Just like before, 3 and 7 are the same dumb thing. So I can switch out 7 for 3. And so what I get is angle 4 and angle 7. They're not congruent. Be careful. Don't get in the habit of just writing congruency signs, okay? It says 4 and 3 are supplementary, so we're going to write 4 and 7 are supplementary. And we do that by subs. And that's what they wanted, right? Ta-da! How you feel? Pretty decent? All right, next one's 2 and 8. 2 and 8. Same side exterior angles. We need to prove them supplementary. Somebody walk me through their strategy. How would you prove 2 and 8 supplementary? Michaela.
2 and 4 are supplementary, and 2 and 6 are corresponding.
You're on the right track, but there's an easier way. That would require a lot of work because you got to switch stuff out. What we want to try and do, Michaela, is we want to try and get 2 and 8 together, right? As soon as possible. So 2 and 4 is a good setup. Does 4 relate to 8 in a really easy way?
Yeah.
Corresponding angles, right? Do you see how that's more efficient? Right, it gets us to the 8 real quick. So 2 and 4 are supplementary, and 4 is the same thing as 8, so we can switch those out, right? That's the plan. That's the plan. Is everybody seeing that? I know the supplementary ones are a little bit weirder. Okay. So I'm going to write that real quick. It says we're going to go with 2 and 4 are supplementary, right? And we know that by linear pair theorem, right? Because they're a linear pair theorem says they're supplementary. Then we know that 4 and 8 are actually, and again, careful how you say that, 4 and 8 are congruent. Oh, I could just write the congruency symbol, you dingus. You dingus. Instead of writing 4 and 8 are congruent, like a Neanderthal. No offense to them. We know that by CAP, corresponding angles postulate. Well, if 4 and 8 are the same dumb crap, whenever I see a 4, I can switch it out for an 8. So 2 and 8 are supplementary by substitution. And we're done. Feeling pretty good? Okay, because that's kind of the heart of the quiz. Let's look at the backside. They give you the AFB and EFD are 65. Now, I'm going to give you a different diagram tomorrow. I am, okay? But it's the same dumb crap. So these guys are all 65. Checks out, right? Probably write that down. They tell you that these guys are lines because they're collinear, right? EFD, EFC collinear. So we do know those are lines. Check the instructions tomorrow, okay? Some of these lines might not look like they're lines. They might look like they're bent a little bit, right? I don't know. There's like an optical illusion here. When you have a bent line like that, it kind of pulls the B with it, and it's like, wait, is that a straight line? Is it not? If they tell you it is, okay? BFD is a straight line. EFC is a straight line. Okay. So BFC and DFE, that's these two angles right here. Are they vertical, linear pair, or neither? These two. Vertical, right? Scissor theorem. And vertical angles theorem says that the angles are going to be what? Supplementary, congruent, what? Congruent. So that's 65 as well. BFA, this guy. DFE, this guy. Yes, they're congruent, but does that mean they're vertical angles? No. It's a coincidence. So it's neither. They're not a linear pair. You might say, oh, wait, look, they're on BFD together, right? But look, there's 3 angles making up that line, right? And those are only 2 of them. So neither. BFC and CFD. So these two. Vertical angles? No! Linear pair? Oh, yeah. They make up line BFD, right? 2 angles on a line, linear pair. It's a flat pair. There they are. How you feel, Chloe? Linear pair. Now, we know by linear pair theorem, those 2 angles are supposed to be what? Congruent? Supplementary? What? Supplementary, right? And what does it mean to be supplementary? What's the definition of supplementary? They add up to 180, right? So if this guy and this guy add up to 180, how much is left over for this guy? $115. The way I would do that in my head is I would say 5 more to get to 70, right? Then 10 more to get to 80. So now I'm at 80, which is a nice number. So I added 15, right? How much more do I need to get from 80 to 100? Or 180, I should say. 80 to 180. How much more do I need? 100, right? So 115. I blew it. All right, AFE, this angle right here, AFC. this angle right here. AFC I'm going to do in blue. This I'm going to do in orange. Duh, bears. Are they a linear pair? This is a tough one, right? Because you might think, nope, there's 3 angles here. Not according to blue. Blue says I am 1 angle. Orange is 1 angle. So together, these 2 angles do make up a linear pair. They do. Just because there's a line in the middle doesn't mean it's not. Doesn't mean it's 2 separate angles. The blue is 1 angle. It's AFC. So they are a linear pair. Now, how big is AFC? Well, by angle addition postulate, I should be able to add those up, right? It's 130. So altogether, that angle is 130. And by linear pair theorem, since these are a linear pair, how much is left over for the orange? 50. So they're a linear pair. BFE. We'll do it in light blue. BFE and CFD. CFD is the green. Here's BFE. Ignore the line here, the ray here. Hi, Ray. Ignore it. Are these a linear pair? Are they vertical angles? They're vertical angles, right? There's the scissors, right? It's talking about this whole angle here. So check it out. If they're vertical angles say that they have to be congruent, right? So the green should be congruent to the blue. So the blue should be 115. Now we can check that. Angle addition postulate says the purple and the orange should add up to the whole thing, right? The blue. Does 65 and 50 make 115? Oh, yeah. Because 60 and 50 makes 110. 5 more makes 115. So that checks out. So BFE and CFD are vertical angles. AFE. AFE. Okay, so that's the orange angle. BFC. Purple angle right here. Okay, so we're talking this angle and this angle. Linear pair? No way. All right, we got 3 angles here. That's not going to work. Vertical? Nah, they ain't. And we know that because they're not even congruent, are they? So, neither. Neither. Find the measure of angle AFE. Well, what is AFE? 50. What is DFC? DFC? 115. What's BFC? 65. How do you feel? Yeah. Knock this one out of the park. You want to do definitions for one? Let's go get those. All right. Let me pick a color I never use. I'm going to use this regular blue. Actually, you know what? We use dark blue. This navy. And it doesn't look like navy, but it is. It is. All right. Transversal. Somebody tell me their definition of transversal, and I'll tell you if it's good enough for me. A transversal is a line. Yeah, that cuts 2 others. Line that cuts 2 others, right? 2 other lines. Yes, ma'am. Yeah, if that's what the that's what, yeah. Yes. If it's on there. Give an example of a transversal. That's the thing everybody forgets. So line T, right? You can either do cursive T, good God. Cursive T, or you can do line T. I'll accept either. Okay, corresponding angles. They're angles that what? Yeah, but that's like using like, what's a bear? Well, it's a bear, right? When you should be saying, what is a bear? It's a pair upside down. Shut up. Shut up. What? Yeah, that are in the same. Not the same, but the same relative, right? Wonderful. Give me an example of corresponding angles. Shelby? 1 and 5. Oh, wow. How creative. Same side. I'm writing way too big. Interior angles. Lord knows if I do put these on here. If I do. I'm not going to put all of them, right? I'm not going to put all of them. You know what your teachers would do? They put all of them on there, and they make it matching. Oh, you get easy points. Yeah, no way. No way. No way. No way. I don't want to know if you can match things. I want to know, do you know it? The best way to figure that out is have you write it out. I like your nails. No, it's going to go in first. Unless it's really bad, which it shouldn't be. I'm hoping this will be nice, like a present to you. Same side, interior angles. So they're in the interior and on the same side, right? So angles that are on the same side of the transversal and in the interior of the parallel, or of the, yeah, we'll say parallel lines. Parallel lines. Yeah. Nah, no. Of the lines, the transversal cuts. Yeah, okay. The reason I don't want to use parallel because we can still have same side interior angles even if they're not parallel. It's just same side interior angle theorem won't be true, right? Because that says if the lines are parallel, right? That's a requirement, stipulation, if you will. So that's same side interior angles. Yes, you are allowed to use the words same size and interior to describe them because you're telling me not just, oh, they're on the same side and in the interior. You're saying they're on the same side of the transversal. Oh, okay, I know what you're talking about now, right? In the interior of the lines, right? Oh, okay, got it, right? That's clarifying. That's a definition. Saying a bear is not clarifying, right? Alternate interior angles theorem. Or not theorem, I should say. Alternate interior angles, the definition. Angles that. What does it mean to be alternate? Opposite sides. All those definitions, by the way, are in notes that I have for you. I didn't tell you guys about this. You don't write any. Or my other class to take all of them yesterday, even though I printed off way too many. Okay, I took them. Okay. This is what we did doing in class. I just had to use one of those, mostly because I don't want to keep track of this. Right? They're all proofs in there. And the picture should help you with that. This is on Google Classroom and Color. I've had them for a little while. I don't want to actually check that. There you go. So that might be helpful. Opposite sides of the transversal. And if they're in the interior of the parallels, right? Or in the interior of the lines that the transversal cuts. And in the interior of the lines the transversal cuts. Now, if I gave you same side exterior angles, it'd be the same definition as same side interior, except what? On the outside of the lines that the transversal cuts, right? Same thing for alternate interior angles versus alternate exterior angles, right? Only difference is going to be that they're on the outside of the lines that the transversal cuts. Here's how I do definitions, if they're on there tomorrow. Does your explanation specifically like lead me to the conclusion that, look, alternate interior angles are 4 and 6 and 3 and 5? If I'm able to take your definition and be like, oh, that's what you're talking about based on your definition, then you've done it, right? Now, if you give me a definition that says something that leads me to believe that, okay, 4 and 6, 3 and 5, and, I don't know, this is a bad example, 4 and 8, right, would fit your definition, that's wrong, right, because 4 and 8 are not. So I don't care how you write it, just make sure it's specific. That's the point of a definition. Let me know you know what you're talking about. Examples as well, something we didn't really touch upon. Give me an example of same side interior angles. Go ahead. 3 and 6 are on the same side. So 3 and 6 are examples. Whoops, numbers are hard. Give me examples of alternate interior angles. Jericho. 3 and what? Same alternate interior. Angle 4 and angle 6. You might say, wait a minute, 4 and 3, opposite sides, right? They're in the interior, but they're a linear pair. Linear pair trumps all. 1 and 7 are alternate exterior, right? Whereas 1 and 8 would be same side exterior. I think you guys got this. I think this is very doable. Should knock this out of the park. I mean, we got the entire review guide done during class. That never happens. Not a lot of material on this. Yes, and I have bins for you. Sorry. I have graded homework in these bins, but you know what? It's fine. It's fine. Yes. Yes, yes. So if you have the theorems that we had through the other day that I'd like you to do it on your own for homework, basically turn that in as well. That's quiz tomorrow. I agree. If you do not feel like this is one you can knock out of the park, come see me. Tomorrow morning, after school, whatever you need. I want to make sure you knock it out of the park. That way I can put this as the last grade in the grade book right before quarter one ends, and it will boost your grade. That's what I would prefer to do. Also, you would prefer to do it because it'll balance out all those other quizzes that weren't so good. Beginning of the year is tough. Beginning of the year is tough. Now we're starting to get to our stride. I feel like most of you guys are being a little more confident with proofs. I think you guys saw that last quiz, quiz 3, the proofs quiz, and you were thinking, oh God, I bombed it, right? And then a lot of you got it back and it was actually better than you thought. Some of you not the case, right? But I think most of you underestimated yourselves. The way you show your work and the way you organize it was garbage, which is why we graded in class mostly, right? But also so you can see that actually, yeah, I kind of do know this stuff. And those proofs are harder than these proofs. Proofs are not going away. That's what we're going to do the rest of the year. It's going to be all right. After we do this, we're going to do some more complicated transversals. Instead of just having one transversal, we might have a couple. We might have a couple sets of lines that they all cut. Ain't no thing. It's got a little bit of algebra in it. And then we're going to move on to triangles. Okay? You get used to triangles because that's kind of, that shapes class. Everything is a triangle. Everything is a triangle. And all triangles are circles. Yeah! Yeah. We talked about the area, right, of a circle and where it comes from? Have we talked about that in here? You haven't, huh? Okay. Got a little bit of time. Let me show you a video that is appropriate enough that I use it. Derivation of the area of a circle. Derivation, derive, it means to pull out of. Education comes from the word derivation, actually. They are derived from one another. They both mean to pull out of, to create, right? To take something and pull out the essence of it, to understand it through, right? So derivation is an excellent word to type in any search engine, whether it's YouTube or Google. Basically, it's just a way of saying, why is the area of the circle pi r squared? Right? The derivation, where did it come from? Right? So type that in. First thing that comes up is this. And this is a beautiful video. This is one of the first videos
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy and hard to read. It undermines the writer's message and the...
Pause and you get this on OBS for the people watching at home. Stare into the infinite, and the infinite stares back. Here we go.
Squared
Oh yeah, we're going to keep the lights on because remember, you can't do the lights on, don't do it wrong.
gives you the area of a circle. But where does pi r squared come from? First, we'll draw a circle and fill in its area. Next, we will divide it into large equal parts and arrange them in a rectangular formation. As you can see, it barely resembles a rectangle. So next, we will divide the circle into small equal pieces, and we will arrange them in the same manner. You can see that it appears more like a rectangle. So if we divide the circle into even more smaller pieces, you can see that every time the shape becomes more like a rectangle.
Like a cone. Really close to a rectangle, right?
So how small must we divide a circle before we can get a perfect rectangle?
Oh, and we're not done.
Well, we can keep on dividing the circle into small, smaller, or the smallest pieces you can make. But the answer is to divide the circle infinitely many times until we cannot distinguish the lines, and eventually the circle can now become a perfect rectangle.
Now, can we ever
So,
divide something
the
like
area of the
this?
circle
Would you
is equal
stop?
to the area of...
No, because infinity is an idea, not a number, right? However, we can theorize about this, right? So if we did, what would happen? Now check it out. Area of the circle is pi r squared. Squared because area is always squared, right? Like feet squared, miles squared, etc., right? There's a reason for that as well, but we won't get into it. Radius is how much it is from the center outwards, right? Now check it out. When we cut up this circle, the side of the pi pieces was the radius, right? And we slid those together. So this is the radius. It's r. Whatever it is, right? Now, when we cut this in half and unfolded it, all those pi pieces, and slid them together, well, what we did is we cut the circumference in half, right? Circumference is the area of the perimeter around the circle, right? And so when we stretched it out, this part is going to be half of the circumference. So check it out. This bit is the radius, right? All these pi pieces here. Love this marker. So that's the radius. This is half of the circumference. Now I told you area is pi r squared. Who remembers what circumference formula is? 2 pi r, right? I always have to remember where the 2 goes. Area is squared, circumference is not. There's a reason for this. Okay? We'll get into it later. So what's half the circumference then? If C equals 2 pi r, half of C is going to equal what? Just pi r, right? Instead of 2 of them, it's just 1 of them. So this is pi r. Do you see it yet? Do you see it yet?
The rectangle, which is equal to base times height. The height of the rectangle, as you can see, is the same as the radius. So height is equal to radius. To find the base, we need to look at the circumference of the circle. And when we compare the base and the circumference, we can see that the base is equal to 1/2 the circumference.
Yeah, because when we unfold the circle, we're unfolding half and half, right?
Remember that the circumference is equal to 2 pi r. When we combine it with 1/2, the 2's cancel out,
By division.
and base is equal to pi r. So now, base times...
What is the area of a rectangle? Everyone knows this. What is it? Base times height. What's our base? Pi r. What's our height? So the area of the rectangle is this. Pi times r squared. It's 2r, right? So the area of the rectangle is this. But we know the rectangle is the same area as the circle because that's how we came up with the freaking rectangle to begin with, right? So the area of the rectangle equals the area of the circle. I just think that looks funny. So that's the area of the circle. It's pi r squared. Archimedes came up with this. Brilliant. Like, how do you find the area of something like that? You turn it into a rectangle. Everything is a rectangle. All rectangles are really fine, and all lines are really curved. Go away! Goodbye. Parting is such sweet.